Hi, Chemistry 12-2. Welcome to the fourth video for week 7. Today we're going to talk about titration calculations, also known as solution stoichiometry. But stop. Before you move any further or continue on with this video, I want you to pause it because Mrs. Tate was nice enough to do a titration lab in her home, and she videotaped herself. And she really did a great job explaining the lab technique of titration and what you can find or what data you can collect through titration. And here's the website for that video, or you could just go to our playlist and you could look up for May 25th titration lab. And please, you need to take a look at that video first and her process of titration before you move forward in this video. So if you want to stop now, take a look at her lab, and then come back. We are going to talk about the quantitative side of titration. So once you collect your data, how can you use that data to continue on and find the concentration of unknown solutions? Okay? All right. So now that you've seen the video, Mrs. Tate doing a titration lab, hopefully you are a little more well-versed in what titration is. We've briefly talked about it. We talked about the setup of titration and the idea of adding acid to base or base to acid and seeing the pH curve when that happens. So now what we're going to do is use that data that we can collect via a titration technique and use that when we look at the quantitative side of things, and that is known as solution stoichiometry. Now in grade 11 you guys probably have talked about two types of stoichiometry, and we reviewed it at the beginning of this semester: mass stoichiometry and volume stoichiometry. And if you recall, Mrs. Tate has this little quick reminder that she uses when she teaches it in grade 11, and that is this mass, mole, mole, mass. And it's easy enough to say, but do you understand what it means? So mass, mole, mole, mass is a very quick way to remember the steps of stoichiometry. I've also listed them down here, so if you want to take a quick look at them, you can. This could also be, say, volume, mass, mole, mole, mass, or it could be mass, mole, mole, volume. So mass and volume can be interchanged depending on what data that you know. And so when we did mass stoichiometry, you will remember we always took the mass of our known substance and we converted it to moles. That was always our first step, okay? I call it the given substance, the substance you were given some information about. Then we did a mole-to-mole ratio, which is really important, and that is comparing the ratio or the moles of coefficients of the substances in your balance equation. It is key to have a balanced chemical equation, and these equations have to be quantitative. Stoichiometry only works with quantitative reactions, so no equilibrium arrows here. All of our reactions will be quantitative reactions, and when we balance them, the coefficients will represent the mole-to-mole ratio. And last, we would convert the moles of our required back into mass or volume, depending on what you were looking for. So solution stoichiometry, you may have, some groups do have a little extra time, so they look at solution stoichiometry in grade 11 as well. You may not have. So I'm going to kind of review what solution stoichiometry is. I'm going to do a couple examples with you, and then we'll take a look at the data that Mrs. Tate collected, and I'll show you how we can use solution stoichiometry to solve for the unknown HCl, which was our secondary standard, and to calculate the concentration of ammonia, which was kind of the end game for the lab. The big difference here is we are going to swap out the mass and put in concentration, right? Instead of just working with masses of substances or volumes of substances, we're going to take a look at both. We're going to take a look at the concentration of substances, and we know that's the ratio of solute to solvent. So how much solute dissolved in solvent? So that's what we're going to take a look at. And we might as well get started. Solutions of ammonia and phosphoric acid are used to produce ammonium hydrogen phosphate. What volume of a 14.8 moles per liter ammonia is needed for the ammonia to react completely? So there's that quantitative reaction with 1 liter of 12.9 moles per liter hydrochloric acid, phosphoric acid. So what you can see here is you can see that we have some chemical formulas which are key, because some of us are weak with producing chemical reactions. And that, if you recall, is the first step of stoichiometry. So these are always going to be the step. Any type of stoichiometry, these are your steps. So the first step is a balanced chemical equation. That's key because we need to have the coefficients correct so that our mole-to-mole ratio will be correct. And so I would pause right now, grab a piece of paper and a pencil, and see if you could come up with the chemical equation, okay, for this substance. And while you're at it, why don't you write down what information we know about each substance. Okay, you're back. Hopefully you tried that, right? If you're just here listening to me, not a lot of learning going on as I ramble on. It's interactive, so when I say pause and try something, you should do that. More learning happens when that occurs. So this is what we have. Now, you may have had trouble coming up with this one. This is a funky product. And nowhere did they say, they gave you the name of the product, but they didn't say it was the only product. So you were probably trying to do a double replacement or a double displacement. And you would have been correct. That's what acid-base reactions are. We mentioned that earlier. Acid-base neutralizations will be a double replacement reaction. This is an exception. I didn't mean to stump you. I kind of forgot. This is an exception. So what you have here are two reactants forming one product. This one, if you guys couldn't predict this one properly, don't panic. You would be given this equation. It's just a little too tough to come up with off the top of your head. Hopefully you were able to do this, and that is label what you know and what you're looking for. Liters is volume, moles per liter. This is a trick from physics. Use your units to help you when you're writing down variables or what you're looking for. So moles per liter is a concentration. You are right. We could also put just molars there. But I'm going to tell you moles per liter is going to actually be a little more helpful. So that's the unit we're going to use. Okay? Your volumes should be in liters. If they're in milliliters, we have to convert to liters. All right? So milliliters divided by 1,000 will give you liters. So this is what we know. I call this my given substance. That's why I put a G here. It's given me two pieces of information about it. I call this my required substance because we're required to find a piece of information about it. We know the concentration, but we don't know the volume of ammonia that we need to completely react. Okay? Remember, when we get to the end point, that's when we've completely reacted, and that means that we have equal moles of base and acid. Okay? Not equal amounts, equal moles. So here's our steps. We've done step 1, balance your chemical equation. Now we're going to move into step 2, 3, and 4. I'm going to use boxes. Really, it is the most easiest of the methods, and I'm going to remind you how to use those boxes as we go. The other thing I want to remind you is this video, or this formula right here. With this formula right here, you'll see we have volume equals moles over concentration, and I'm just going to rearrange it because that was incorrect. Concentration, well, it's correct, but it's not the format I wanted it to be in. Concentration equals moles over volume. So whenever you're looking for the concentration, you have a ratio, your moles of solute over your volume of solution. And we can rearrange this formula any way we want. If you notice step 2, it says convert given to moles. My given substance, I know the volume and I know the concentration. How can I find moles, right? So it's concentration moles, that's our first, then moles, then concentration. So you can rearrange it by actually bringing your V right up here. So you see V times C will give me the moles of my given. And I happen to have those. So that's how we're always going to start out our boxes. When you do solution stoichiometry, you always start your boxes with the volume of your given. So I have the volume of my given right there. And I have the concentration, and I'm just going to put them right beside each other, okay? So they're on the top boxes there, right beside each other. The units do factor out because you'll see if I write moles per liter, I could also write moles on the top and liters on the bottom. That's the same thing as moles per liter. And you can see how the liters are going to factor out here, okay? So we've done our concentration to moles, right? So concentration is what we had. Using the volume, we converted it to moles. Next step is mole-to-mole ratio. The mole-to-mole ratio is your coefficients up here. So you'll see that my required has a coefficient of 2, and my given has a coefficient of 1. So now we have our mole-to-mole ratio. Okay? The given is always on the bottom. The required is always on the top. Or you can do your moles. So this here was my given. So this was moles of H3PO4. So I'd have to put moles of H3PO4 down here to factor out. And this would be moles of NH3. It has a 2-to-1 ratio. Okay, so concentration of moles, moles to moles, and then we have our last one. And our last one here is converting it back to volume, right? We wanted to find the volume of our ammonia, so we're converting it back to volume. A lot of people get stumped on this last one. They're like, why did you put this down here and not here? But use your formula. So if we're looking for volume, we divide both sides by C. So you'll notice C is on the bottom of our ratio. So that's why I put C, or concentration, at the bottom here. It kind of looks weird because I put moles and the liters on top. You know, if you left that blank and put moles per liter down here, I could live with that. But it goes to the bottom box down here, and that's important to remember. So calculate, we multiply the top numbers, get an answer, divide, and then open up a bracket. Put all of these bottom ones in a bracket, multiplying them, and then an equal sign. And that is the volume that you find. Let's try one more. Here we have an example, okay, and I'm just going to cover it up so we can see it maybe one at a time, or a little bit at a time, I should say. It says, as part of a chemical analysis, a technician determines the concentration of a sulfuric acid solution. In the experiment, 10 milliliter sample of sulfuric acid reacts completely with 15.9 moles per milliliters of 0.15 moles per liter of potassium hydroxide. So they are doing a titration. So in their Erlenmeyer flask, they have sulfuric acid. So they've put 10 milliliters in their Erlenmeyer flask. And in their burette, they have potassium hydroxide. So they've put the acid in the Erlenmeyer flask, and they have potassium hydroxide in the in the burette. And they put their indicator down here with sulfuric acid. And we're starting with a strong acid, okay, and we're moving to a strong base. And so our pH curve would start low, and then when it hit the end point, it would rise really quickly, and then it would flatten out again. Okay, so they did a titration to get this data. Remember your steps. First step, balance chemical equation. So when you balance the chemical equation, this one's a little easier to predict. Okay, so stop now, look at the players, come up with a chemical equation, balance it, and write down what you know for each of your substances. Again, I hope that you did pause, and I hope that you did come up with your chemical equation. It is a double replacement, which we would predict. It's an acid-base reaction. It's a neutralization. And when you put them together, right, we have our sulfuric acid. Remember, we have our acid table. So if you're going, man, sulfuric acid, what's that again? It is an ick, so it's sulfate, but you could check your acid-base table if you need to, right? You'll always have that handy. And we have our KOH. And we have our KOH, and when we balance those out, we get HOH, which is water, and K2SO4. So it's a true double replacement, okay? If you put your information there, and that's how I know my R and my G, if you put your information there, we see that we have our volume. I converted it to liters. Remember, divide by 1,000, convert it to liters. I'm looking for the concentration of H2SO4. I have my volume of KOH. I got that by doing a titration. And I have the concentration of KOH, okay? And so KOH was in the burette. So they would do many trials, but they would take the average volume, the amount needed to get to that endpoint, okay? And, oops, we want to find the concentration. So we have concentration of this guy. We want to find concentration of this guy. We know our liters. That screams solution stoichiometry, okay? So let's see if we can remember. Oops, bring that down again. Get a little carried away. Our formula here is going to help us get started, and that's why I always put it right here in our steps. So we've got our balanced chemical equation. Now we want to convert our given to moles. So this is our given substance. We know our volume, and we know our concentration. We need to get it to moles, right? Concentration, moles, moles, concentration. So if we rearrange it, V and then C. So that's how our boxes will start out all the time. And we have our liters, okay, and this is our given. So we start with our given, and we have our concentration. Okay, the liters of KOH would factor out, And we have our moles up here. So we've gone from concentration to moles. Now we do our mole to mole ratio, right? And our mole to mole ratio, if you remember, given on the bottom, required on the top. Or you can remember this was moles of KOH, so we have to put moles of KOH down here so we can factor out. It's a 2-to-1 ratio. 2 is on the bottom, and that's key, remember, with stoichiometry. Our last step, okay, we want to get back to concentration. So if we use our formula again to help us out, this is how we find concentration. Notice that the V is on the bottom, and that's what we know about H2SO4. So we put it on the bottom as well, okay? I'll give you a heads up. We're always putting, that last step is always on the bottom, right? We kind of sometimes leave this top blank. We're always putting our information on the bottom. But the reason why is because of that ratio, okay? Moles over volume. So we calculate this out. We multiply our top numbers, get a total, hit the divide button, open up a bracket, get a total for the bottom in that bracket, and then hit your equal sign. And we get our moles per liter. So hopefully, and that was quick, but I wanted to also get the lab done. So I wanted to show you a couple examples of solution stoichiometry, show you that it's very similar to any type of stoichiometry. You're just starting with concentration and finishing with concentration or volume. Okay, here we were looking for a concentration. Last example, we were looking for volume. A couple things to remember about titrations. Some terms there. Mrs. Tate hit on most of those when she was doing the example. You can also read your textbook. Titration is just a lab technique, right? It's an acid-base reaction, slowly adding one into the other so that we can get to the end point where the moles of acid equal the moles of base, so we neutralize it. Titrant is what we put in the burette. End point is when we have equal moles of our acid and base, right? So we have that end point. pH is often how we measure our endpoint. Equivalence point is volume. So how much of your titrant did you have to add in order? So it's a volume measurement in order to find your endpoint. And standard solution. So a standard solution is a solution where you know the concentration. So in the lab, when we were looking for the concentration of NH3, ammonia, we had to do 2 titrations. Our first titration was actually to standardize our HCl. So we had to do a titration just to make sure we knew exactly what the concentration of our HCl was. Then we can use that in order to find the concentration of ammonia. So standard solution. Mrs. Tate also talked about a primary standard. And a primary standard is, actually there's 3 key things that are true about a primary standard. The first one, well, I mean, if you can get it, that's important. But these last 3 bullets are the important ones. Does not absorb water when exposed to air. So some solutions, what they'll do is they'll absorb water from the atmosphere, and that water will cause the concentration to shift. And so we are looking for a standard. So we don't want our concentration to shift at all. So a primary standard is key that it will not absorb water from the atmosphere. It is also non-reactive. We don't want it to react with anything else that might be in the water, so we want a very low reactive substance. And the third is if it has a high molar mass, it's even better. The higher the molar mass, the better. And I'll give you an example. Mrs. Tate uses Santa Claus and a baby to demonstrate this, and I thought that was brilliant. So I'm going to show you or explain her explanation here. Santa Claus is about 300 pounds. Baby, when a baby's born, it ranges probably from 6 to 11, 12. Those are big babies. So let's say a 10-pound baby. So what moms and doctors are very key on in the first months of the baby's life is how much weight they lose or gain. And if you think about it, if this little baby lost or gained a pound, that's 1/10 of its body mass. So that's a big deal. When you have a small amount, even a tiny change in mass can make a big difference. Over here with Santa, you've got 1 pound more or 1 pound less, not really going to make a big difference. The bigger the mass, even if you mess up a little bit and you don't measure your mass completely correct, it's not going to affect the overall concentration that much. The same is true with solutions and with the molar mass of the compound that you're making the solution with. So we used sodium carbonate as our primary standard, and it was a better primary standard than HCl. We actually used it to find the concentration of HCl. If you compare their molar masses, 106 compared to 36.46. So when we take a look at sodium carbonate, even if we measured incorrectly and we were off about, a gram or two, it wouldn't really change the concentration of the solution that much because it's a large mass. Over here with HCl, if you're off a gram, it can change the concentration quite a bit, and that'll throw all the other titrations that you're going to do with that HCl. So I just wanted to let you guys know that, just because you'll be brilliant in first-year university when you're doing titrations. But a primary standard is a little different than just a regular standard, okay? Finally, here we are. I'm going to do this in 10 minutes or less. So this is the titration lab that Mrs. Tate did for us in the video. She gathered lots of information. She did 3 trials for her first titration and 3 trials for her second titration. And so I've gotten the data, and what we're going to do is we're going to analyze that data using solution stoichiometry. So titration is gathering the data, and solution stoichiometry, sometimes people call it a titration calculation. It's actually quantifying that data, okay? So use solution stoichiometry to determine the concentration of the secondary standard. So remember, our primary standard was this sodium carbonate. Why? It had a large mass, molar mass. It does not absorb water from the atmosphere. It's readily available, and what was the other one? Readily available. It's large molar mass. It doesn't absorb water from the atmosphere, and non-reactive. Okay, so it's not going to react with anything. So those are the things we look for, and that's a really good primary. HCl, not so much. HCl actually does absorb water from the atmosphere. And so if we leave HCl out too long, its concentration is going to change. So that's why it's really important to standardize HCl first before we use it. So we had 2 steps. Part A was using sodium carbonate to standardize HCl to make sure we knew the exact concentration of it. And then part B was using that exact HCl concentration to find the concentration of NH3. Okay, so a 2-step. If you recall how she set it up, it's kind of like that. She had her burette. She had her HCl. It was the titrant in her burette. She had a stopcock, which is opening and closing the burette. Her Erlenmeyer flask, that's where she put the primary standard, the sodium carbonate. Okay, so that's kind of the setup that we had. Now, a couple things we should know about it. What did we know about our sodium carbonate? It was our primary solution. She used 1.52 grams of it. I don't know if you picked that up, but she did, 1.52 grams of it. And she made 100 milliliters of it. She did a nice little review of how to make solutions as well at the beginning of her video. And so what we're going to do is we're going to have to find out, we know mass, we know volume, we need to know the concentration, right? This all rests on the concentration of your primary solution. So your first step here is to take the mass of sodium carbonate and its volume to find its concentration. Now, do you remember how to find concentration? If you recall, see if it's going to let me move this over this way. Yeah. No, I'm just going to show you. This is how you find concentration. You need to know 2 things. You need to know the moles of solute and the volume of solution. Well, we know the grams of solute, not the moles. So our first step is to take the grams of sodium carbonate, using its molar mass, converting it into moles. Okay? When we were in grade 11, one of the big mistakes we often saw is that someone would just put 1.52 here and 100 mils here, and they wondered why their answer was incorrect. Well, N stands for moles, so we have to take our grams of sodium carbonate, divide it by its molar mass, and we get our moles. Okay? Then we have to take our volume, but our volume here is in milliliters. We have to convert it to liters. So divide by 1,000 to convert it to liters. Now we're ready. So if we want to find our concentration, we can take our moles and divide by our volume. Okay? And if I clone that maybe, we've got a nice little equation there. Okay? So knowing where the numbers come from sometimes is helpful. So before we could do anything, we had to find out the concentration of our solution, our primary solution. So that was kind of our first step that we'd have to do. Now, I'll get that answer there for you in a second. But if you remember stoichiometry, our first step is to balance chemical equation. So what is our balanced chemical equation going to be? Stop for a second. What will be the reaction between sodium carbonate and hydrogen chloride? Balanced chemical equation. Okay, you're back. Here's our balanced chemical equation. Okay, it's a double replacement. It's an acid-base neutralization, how we predict. We've balanced it with a 2 and a 2 there. We also now know, because we did a little bit of work, what our concentration is. So I did find an answer up here. The answer to that is 0.140. Okay, so I just put that down here. And we're going to use 10 milliliters each trial. So we've got our 10, I changed it to liters though, so I don't need my milliliters there. So I changed it to liters, okay? The whole reason why we're doing part A is to find the concentration of HCl. And this is actually introducing something new. So the two examples we did up to this point, they would have given me this volume. And you might not have known where that volume came from, okay? Because it's the titrant, it's the burette. But you recall in the video of the lab that she would take initial readings and final readings, and she would use her indicator in here, and she would add just enough HCl to change that color. And then she could measure how much of that HCl she put in. And she created a data table. Okay, so this we knew because we knew the volume and we knew the mass, so we were able to find the concentration. Each trial we used 10 milliliters, so we know the volume. Over here we're looking for the C, but what Mrs. Tate created when she was doing those 3 trials is a table that looks like this. And you might have noticed on your assignment that the last 6 questions, some of them involve a table. And when the last 6 questions, what you're going to be doing is you're going to be doing solution stoichiometry to solve those problems. But some of them have a table, so they're giving you a data table. So you need to know how to read the data table and to see what information that data table is giving you. So here you can see the 10.00 milliliters. It's really important to read the title of a data table, and that's because it's going to give you a indication of amounts and substances that you're using. So titration of 10 milliliters of sodium carbonate with HCl. Remember, with HCl means it's in the burette. It's telling us how much of the sodium carbonate. They might not mention that in the question, so read your table to see, title to see what's happening. So Mrs. Tate did 4 trials, and she took a measurement when she started. And there's a reason why I put initial here and final here. That messed people up, but we put initial here and final here because of subtraction. So initially, she would take a measure, and our burettes are 2 places after the decimal, so she read them carefully, 2 places after the decimal. And so she was able to make a measurement before. You don't have to start at 0 all the time, right? You can take a note of where you are and where you finish on your burette. Then she added just enough so that she got her color change, so she reached the end point. And when she reached the end point, she'd take another measurement, and she measured at the final burette. So for her first trial, she started at 0.2. Remember, they start at 0 and go down to 50. She started at 0.2, and she went all the way down to 13.40. Her second trial, she started at 13.40, right? And she went down to 26.20. Her third trial, she started at 26.20, and she went down 39.00. Okay, now she was getting close to the end, so she topped it up again, and she started at 0.4 for her fourth trial and went down to 13.4. She was worried that she'd go too far past the 50 here, so she stopped and refilled her burette and started at 0.4 and went down to 13.30. Really important that you know how to read one of these tables, okay? So initial reading before she starts adding the titrant, final reading after she's finished adding the titrant, looking for that endpoint, looking for that color change. The first time she might have not been paying close attention, so she overshot it. So it got way too orangey pink. And so she knew that that probably wasn't a great trial. But the last 3, 2, 3, and 4, they were really good trials. So some tables will tell you if the trial was good or not. Some tables won't. They'll just write down the trials. We call this an outlier. So we're not going to use this in our our calculation. And that's important. If you have many trials, you find your best three. That's what you want, the best three trials, okay? We'll leave this information out because it wasn't a really good trial. So what we can do with this is we can calculate all of the amount. So in total, how much for each of them. So here we can calculate it. It's going to be 13.20, okay? We can use it, but we won't because it's not a great trial. The other is 12.80. And what I'm doing is I'm just subtracting these two numbers here. That's how I get the overall change. Here it's 12.8. Oops, that's not where I want it. Get it in the right table. 12.80. And here it's going to be 12.90. Ugh. When I'm hurrying, that's when this happens. All right, so we get 12.9. Good idea. Oh my goodness gracious. I am back. I just had to pause for a minute so you didn't hear me freak out about trying to get this into the right font. So 12.90 is going to be, when I subtract those two numbers, I get it. So we can see that I cross this out because 13.2, 12.8, 12.8, and 12.9. You want to have the three trials that you're going to use within one or point, usually within one, actually I should say within 0.1 amount or decimal place for them. So these three are your best examples to use here. And so what I did is I wanted to find the average of those three because I need one volume, not three volumes. So I take the trial 2, trial 3, and trial 4, and I add them together and divide by 3. So I get an average here. Okay, so this is my which used to be there. Average volume of HCl. Okay, so it's 12.83. So Mrs. Tate did everything in the lab to come up with this. This is what she was able to get in the lab. Now, we have to use that 12.83. Now, that's in milliliters, so I'm going to bring it up. So the volume is actually 0.01283, okay? And that's going to be liters. So we use our table to find the volume of our titrant. And this information is found by doing a titration. So you should be able to read a table like this and gather the information you need to gather. Now it's pretty quick. It's just like solution stoichiometry that we did before. This is going to be our given. We know two pieces of information. This is our required. We're required to find the concentration of HCl. So we bump down here. Remembering our equation, we're going to use boxes. So for solution stoichiometry, our first is to change our concentration to moles. So if you recall, we bring our volume up here, and we're going to start our boxes with our volume. Okay? So we take the volume of our given, and our given here is sodium carbonate. We multiply it by the concentration of our given, which is sodium carbonate. Okay, we're not going to get an answer yet, but we've got our concentration in moles. Then we do our other moles, concentration, moles, moles. So it's our mole to mole ratio, our given substance on the bottom, our required substance on the top. These come from the coefficients of the reaction, right? See, 2HCl, 1Na, 2NaCO3. And we can find that we have, oops, I didn't want to show you that yet. So we have our mole to mole ratio. Then we want to find concentration. So when we find concentration, what you'll see, if I recall, that if we bring that up here and we want just the concentration, if I bring my volume back down, my bottom box is where I should put the volume of my HCl. So that's what I got out of my table, the volume of HCl. So if you multiply the top, get a total, divide, open up a bracket, multiply all the bottom, close that bracket, and equal, this is the concentration you get for HCl. And this is important to go on and finish part B, because part B is going to be about using this now as my secondary standard and using this concentration in order to solve for the ammonia. So very quickly, I know I'm over time, but very quickly to finish up part B, we used HCl as our titrant. We have our ammonia in here now, so we've changed out what's in our bottom beaker. We know the concentration of this now. We just standardized it, so we found that concentration. We are looking for the concentration of NH3. We have our equation, and this is kind of an odd equation because it's breaking up into its two ions here. Okay, we have an exchange of H, so it's a little different. It's not a double replacement. We have our required and our given. We have our volume because each trial used 10 milliliters of that. But again, table here, guys. So whenever you do a titration, that's why you're doing a titration. So everything Mrs. Tate did was used to find volume. We then have to go ahead and use stoichiometry to solve it. Here's the table again. See if you're okay with reading this table. You might want to pause right now and see if you can fill this table in and finish this equation or this problem on your own. And if you want to tune back, we'll correct it. So here's the table again. Remember, the title is important. Titration, 10 mils sodium or ammonia with HCl. So we have HCl. We are, this is a weak base and this is a strong acid. So we're going to have an endpoint higher than 7. We would start our pH level, our pH curve would start high, not as high as 14, it'd be a little lower. So here again, final and initial. This is so when she did her first trial, she started at 0.4. She went down to 11.80. It was a good trial. She reached her endpoint. Then she started 11.3. And she went to 23. I'm guessing this would be, I think that might have been a typo on my part. So let's just do that. 11.80. And you've got 23.20. And then she started at 23.20 and went down to 34.50. Okay? So we want to know how much was added for each trial. So what we do, and that's why we set up the final on top and the initial on the bottom, we subtract them. So here we're going to get 11.40, and here we're going to get 11.90, and here we're going to get 11.30. So subtracting, but then taking the average. So add, divide by 3, and our average works out to be 11.53. There, 11.53. Now that's in milliliters, so be careful. We're going to have to convert that, right? 11.53. So we can come back up here, and that's how you read the table. So the table is what you're getting from your titration, and we're using that, and we'll put that into liters up here. Okay, so we've got our players. Now all we have to do is our solution stoichiometry, right? So this is our given. And that's how the table helped us out to get this volume. That's why we did titration, to get this volume. Now we can use solution stoichiometry to find our unknown. So we're going to use our equation like we did before, right? We want to start with volume, right? We want to find moles. So concentration moles, moles concentration. So we're going to find our volume of HCl. We're going to multiply it by our concentration per liter. We're going to do our mole-to-mole ratio, given on the bottom, required on the top. It's a 1-to-1 ratio. And we're looking for concentration again. So if we move that volume back, we put the volume of our required on the bottom. And we get our answer, 0.251. I'm sorry I went over, but I wanted to finish this up for you. Hopefully now, watching the lab demonstration and watching me do a few of these solution stoichiometry calculations, you should be set to do part C of your assignment. Thanks so much.